The fundamental theorem of calculus. There are two parts to the fundamental theorem of calculus. Part 1 says that every function has an antiderivative function, which itself can be differentiated. So it shows up like this. The derivative of an integral. So if I start with f of t and I integrate it and then differentiate it, I'm going to generate my original f function. So this represents part 1 of the FTC, or the fundamental theorem of calculus. The other part of the fundamental theorem of calculus, or part 2, states that the area underneath a curve is equivalent to the displacement on the antiderivative function. So how does this show up when we do some problems? So if I take a look at this example 1, we have first the integral. So we have the integral in here. And then we're going to differentiate that integral. So if I first apply the integral here, so I have d by dx, and integrating sine x, I'm going to end up with negative cosine, and I'm going to integrate that from its bounds of 0 to x. I'm going to put that into the bounds into this integral, and so I end up with an expression that's going to look like this: negative cosine of x, when I substitute in the x, minus negative cosine of 0, that happens to be 1. Okay, regardless of what this value is here, it's going to be a constant, and when I differentiate it, the derivative is going to give me, the derivative of negative cosine is going to be sine x. Okay, so basically I started with sine t in the integral, I integrated it, and then I applied the derivative to it. And when I do those two parts, what I start with is what I end with. So I ended up with a sine x as my final result. So again, we can see that as I integrate and differentiate, I end up back where I started. Now, there is this issue of the t here, and really we use this variable t instead of x that we don't conflict with, so that we're not going to conflict with the bound variable of x. So that's why there's a t and a dt here. Okay, so let's try this to see what happens here. So I should expect to end up with the original function that I start with. So I'm starting with, this is my integrand, and I'm going to integrate and differentiate. So I should end up back where I started. So again, applying this, here's my integral expression. So I'm going to do that inside first, so the integral first. So d by dx, the integral of, in this case, I'm going to use the antiderivative tan of t, and putting in the bounds from pi over 4 to x. I'm going to apply the bounds to this expression. So I'm going to do the derivative of, I'm going to plug in my x and my pi over 4, so I get tan x minus tan pi over 4. Tan pi over 4 again is a constant value. Okay, so this represents some constant value. So when we differentiate that, it's going to differentiate to 0. So the derivative of tan is secant squared. And I end up back where I started. Okay, so I started with a secant squared, and I ended up with a secant squared. Okay, so this is kind of what I expect. My derivative and antiderivative, or my derivative and my integral, are going to undo each other, and I'm going to end up with what I started with. So let's take a look at another example here. Now, in this case here, we cannot anti-differentiate tan t. Okay, we haven't learned how to anti-differentiate this yet. So, but although we can't anti-differentiate this, what we're actually trying to find is where the integral is going to be g of x, and then we're going to differentiate g to get g prime. Now, we can't find g of x, so can we find g of x? No, we can't find g of x. So the answer to this is no. But if we apply this, we know that an antiderivative does exist. So we know g of x is going to be equal to, okay, if I take the area under that curve, if I anti-differentiate that, I'm going to end up with big F. I'm going to call the antiderivative big F, and I'm going to evaluate from 0 to x. That's going to be just f of x minus f of 0. Again, f of 0 is a constant. And if I want to apply g prime is going to be the derivative of g, which is big F of x minus big F at 0, which is a constant. And when I differentiate that, well, the derivative of big F is just going to be my tan. So I end up with tan x. And then when I differentiate minus f of 0, I'm going to get 0. It's going to differentiate to a constant. So again, notice that I started with tan t and I ended with tan t. And although I didn't know what the antiderivative of tan is, I know it exists. And I also know that when I differentiate, I'm going to get back to tan. So again, we can see that the derivative and the antiderivative, or the derivative and the integral, will undo each other. So again, we can do the exact same thing here. But we can just kind of skip these steps now, because we know that if I integrate and differentiate, I'm going to end up back where I started. So in this case here, again, we're going to start with this integrand. We're going to integrate it, and we're going to differentiate it with g prime. So can we find g of x? No, we cannot find g of x. We do not know how to anti-differentiate this complex function. Okay, so the answer here is no. We can't find g of x. Do we need it? No, we don't need it, because we're just going to apply the fundamental theorem of calculus. So in this case here, we know that antiderivative does exist, and when I differentiate it, I'm going to get back to my integral, which is going to be 1 square root of 1 plus t cubed, but I'm going to embed my x into my t, and I'm going to end up with what I started with. So this is the application of the fundamental theorem of calculus. When I differentiate and integrate, I'm going to end up back where I started.